Welcome to The Explainer. Today, we're going on a massive journey. We're mapping out the future of scaling climate technology. Specifically, we're looking at this incredible, transformative leap from early pilot projects, like the Stratos plant down in Texas, all the way to the gigaton-scale global carbon removal infrastructure we desperately need to secure our future. It's a fascinating look at how we're actually going to clean up the atmosphere. Let's get right into it. Before we dive deep into the tech, I want you to picture the climate crisis as a bathtub that's dangerously close to overflowing. For decades, the entire global focus has basically been on the faucet. How do we stop the flow of new emissions? But as that water level creeps higher and higher, we really have to ask ourselves, is it enough to just turn off the tap? Or do we actually need to pull the plug and start draining the tub? Okay, let's dive into this because it's an absolutely crucial distinction. On one side, we have carbon avoidance. That's turning off the tap. It means preventing future emissions from getting out there in the first place, like swapping out a dirty coal plant for a clean wind farm. That is absolutely essential, no doubt. But it doesn't do a single thing about the water that's already in the tub. On the other side, we have carbon removal. This is pulling the plug. Removals physically extract the legacy CO2 that's already trapped in our atmosphere, driving climate impacts, and then locks it away permanently.
Here's our roadmap for today's explainer. We'll start with the carbon cleanup mission, look at our technological vacuum cleaners, check out the first pilot projects, tackle the massive energy challenge, and finally, chart out the gigaton scaling roadmap.
All right, part one, the carbon cleanup mission. And this brilliantly illustrates the sheer scale of our mission. Achieving true net zero isn't just about peaking and cutting emissions, turning off that tap. It requires building a massive new wedge of carbon dioxide removal. The science is incredibly clear here. We need massive carbon removal to balance out those really stubborn, hard-to-abate sectors, like agriculture and aviation. And eventually, we need it to bring all that legacy atmospheric CO2 back down to much safer levels. Moving right along to part two, our technological vacuum cleaners. First up on the tech roster is direct air capture, or DAC. Think of these as giant industrial vacuum cleaners for the sky. They use highly specialized chemical or physical processes to suck carbon dioxide directly from the ambient air around us. Now, this is technologically staggering. Why? Because it requires pulling CO2 from air where the concentration is incredibly low. We're talking only about 425 parts per million. That is just over 0.04%. It's the ultimate needle in a haystack problem, which, as you might guess, makes it super energy intensive. Now, another heavyweight in our toolkit is BEACS, which stands for Bioenergy with Carbon Capture and Storage. Instead of trying to pull from the thin open air, BEACS captures CO2 straight from the flue gas of an industrial biogenic process, like burning biomass for energy. Because the CO2 concentrations pouring out of that smokestack are way higher than just normal ambient air, it's currently much cheaper to do than DAC. In fact, right now, BEACS is the largest scale, durable, engineered carbon removal approach we've got. Now, what's really interesting about this is the contrast in how we approach the cleanup. On one hand, we've got these highly engineered atmospheric solutions like direct air capture operating out in the open sky. But on the other hand, we absolutely have to leverage nature-based and hybrid approaches too, like biochar. That's where you convert organic material into a super stable form of carbon that can just be locked away in our soils for centuries. The truth is, there's no single silver bullet here. We're going to need a massive, diverse portfolio of both to pull this off. Which brings us to part three, the first pilot projects. Okay, I want you to just focus on this number for a second, 500,000. That is the impressive annual tonnage of CO2 that the massive Stratos plant down in Texas is designed to extract once it turns on. Built by 1.5, it is set to become the world's absolute largest direct air capture facility, securely locking all that carbon away in deep saline aquifers. But here's the kicker. 500,000 tons at Stratos, that's really just step one in a much larger transformative journey for our global climate infrastructure. And Stratos isn't flying solo here. Look at these early pioneers mapping out our future. Over in Rotterdam, Flare Electra is running solar-powered technology that drastically cuts down energy needs. Up in Iceland, Climeworks has their Orca plant, which brilliantly uses the Earth's natural geothermal energy to literally turn CO2 into solid basalt rock. And in Alberta, Canada, Deep Sky is building a whole multi-technology testing hub. We're seeing this incredible burst of global innovation, testing out different energy sources and chemical processes to see exactly what scales best. All right, part four, the massive energy challenge. Now, let's be real for a second. When we look at the energy requirements across the scientific literature, the laws of thermodynamics are pretty unforgiving. The theoretical absolute minimum energy just to extract and compress CO2 is over 300 kilowatt hours per ton. But real-world DAC, it requires significantly more energy than that. You've got to run the fans, heat the solvents, power the compressors. Moving a million tons of air just to get a tiny fraction of CO2 takes an absolute massive amount of power. So the crucial point is this: scaling carbon removal isn't some magic trick. It's a rigorous thermodynamic and infrastructural challenge. Pulling dilute CO2 is always going to carry an energy penalty. Building these massive hubs requires huge land footprints. And critically, these plants have to run on zero-emission energy. If we aren't super careful about this, powering thousands of DAC plants could actually compete for the exact same renewable energy we desperately need to decarbonize our normal electrical grids. And that leads us to our final chapter, Part 5, the Gigaton Scaling Roadmap. Remember that 500,000-ton number from the pilot project? Well, I want to draw a stark contrast by revealing this staggering figure: 10 billion. That's 10 gigatons of CO2. That is what scientists estimate humanity might need to remove every single year by 2050, just to stay within safe temperature limits. Bridging the massive gap from early pilot plants to 10 gigatons is the ultimate, transformative journey for our climate over the next 3 decades. We literally have to go from today's thousands to tomorrow's billions. Let's see how this builds, because right now we're at the very, very beginning of this trajectory. We're moving less than 0.1 gigatons globally with engineered solutions today. Scaling from that tiny sliver of capacity up to that towering 5 to 16 gigaton target requires an absolutely massive growth curve. It's a multi-decade journey. It's going to require the kind of intense, sustained investment and rapid deployment that we saw during the early days of the solar and wind power booms.
So how do we actually walk this path? Well, first, we validate the tech through those pilot projects we just talked about. Second, and this is a big one, we establish robust rules. Just recently, the EU adopted the world's first voluntary standard to certify permanent carbon removals. This is a game changer for combating greenwashing and building the market trust needed to unlock billions in investment. Third, we secure the massive amounts of low-carbon energy to run these plants. And finally, we scale the whole operation to gigaton capacity.
We're truly witnessing the birth of an entirely new global industry, and it's one dedicated not to taking from the earth, but to healing the atmosphere. We've built the first vacuums, and they're turning on right now in places like Texas, Iceland, and beyond. Yes, the technology is real, and sure, the road ahead is incredibly steep, but the destination is a stabilized climate. So I'll leave you with this: we've built the tools. Are we ready to clean the sky? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you next time.